What's up, guys? So,
Hey, everyone.
we are talking about Stephen Wolfram's path towards the physical theory.
Everything.
Theory of everything, yes.
Yeah.
So, this is one that is kind of overdue.
It is.
It came out, a few months ago.
Beginning of quarantine, maybe?
Yeah. Somewhere around there.
Yeah.
So, so we just talked about, a little bit about what it is, about Stephen Wolfram's background. We got a little sidetracked, talked about computing, what are computers. And we brought it around again, talking about the general relativity, special relativity aspect of the theory at the end.
Yeah.
And
then we sprinkle in our thoughts, too. I guess this is kind of like a first impression of sorts, right? Of the theory, I would say. Like, because we kind of just went into it and just kind of like did like a quick little dive into some of the work. So,
absolutely.
Our general first impressions. It's not like a deep dive where we're like...
Yeah, so if any of you experts out there, you might want to skip this one.
Or criticize, or leave comments and stuff, or hit us up on our Twitter.
Yeah.
At
So,
Eigenbros.
Yes, of course, guys. So make sure to like, subscribe, share, comment, and then check us out at Twitter. That's Eigenbros on Twitter, Eigenbros on Instagram. We have Eigenbros2 on TikTok, and then also Eigenbros.com. And we'll see you guys in a little bit.
3, 2, because you got a countdown, bro. 3, 2, 1. Welcome everybody to the Shadow Realm.
Ooh, the Shadow Realm.
Yeah,
Why? This is dark.
This is because No,
hopefully we can color correct that in the post.
Oh, probably. Yeah. I'm just saying the Shadow Realm because look at me. I'm disheveled. I'm living the grad student life right now.
Still look probably better than me, so it's okay.
Nah, we both got gray shirts. That's how you know somebody's going through some shit. Like we're just wearing gray. We're wearing gray how we feel inside. You know what I'm saying?
It's a rainy, dreary day.
Yeah, rainy, dreary day. We we were reading some stuff by Wolfram, and it made us even more depressed because there's not a good enough theory out there to describe the world in any meaningful way. No, I'm just kidding. No, you actually put it on. Actually, a couple listeners put it on our radar to kind of just do this, right?
Yeah. So some people asked us if we can do a review on the Wolfram Physics Project, and I, ever since even when Wolfram came out with it, I thought that'd be a good idea. But of course, I just was dreading it because I knew I'd have to learn a bunch of shit that I didn't know anything about. Because Wolfram's background is he's actually, it's interesting. His background's particle physics, but he's generally seen as like a computer science guy nowadays in many ways. So I was like,
computational. Well, true. He a computer science guy, right? It was not even computational physics in any way, right?
I guess you could say computational bit, because I mean, for those of you not familiar, Stephen Wolfram is the inventor of Wolfram Alpha in Mathematica, and that's got some high level computer science. I don't know what you would even call it, algorithms or something involved in it in order to be able to do really intense calculations. I mean, physicists, engineers, mathematicians, we all use Wolfram Alpha / Mathematica to do research. So it's a big undertaking that Wolfram did to make it possible.
Yeah, I remember in undergrad. Where were you when you first heard about Wolfram Alpha?
I was definitely one of the first people to know about it, for sure.
Yeah, a couple of my friends too. We were like in Cal 2 or something, and we were like, dude, you can just check this integral with Wolfram Alpha. And I was like, Wolfram Alpha? What the hell is that? And and then you just you plug it in, you plug in your integral, and then it shoots out even if it's definite or indefinite, you just throw it in there, and it just cranks out a response, and even gives you like nice little like alternate forms and stuff. It's really nice. But yeah, this is probably early 2010, maybe 2011.
Yeah, I guess it was about there, right?
Yeah.
I remember back in the days when it used to actually tell you the steps of the problem still.
Oh, yeah.
To pay. Remember
when it was free,
Yeah. I was so sad when he took that feature behind a paywall.
Same. Unless you were smart like me and paid for the app early on, and now you just have the...
Oh, you're grandfathered in.
I'm grandfathered in.
See, I got the app when it was free on the Amazon store, but then now they're making me try to log in and stuff, and I can't use it anymore. So I'm like, damn it.
Mwah.
Yeah.
Yeah, I know. That's how they get you, though. But I bought the Android one, and then I've been seeing the steps ever since.
There you go.
Anyway, shout out to Wolfram for making
Yeah.
calculus easier to get through.
Mhm.
But that's not the only thing. That's not his like biggest contribution. I think if this theory is expanded on more and then it becomes more testable in some way, I think this would be probably his biggest achievement. I think he wants it to be, right?
Yeah, I would imagine so, right? Because it's kind of a well, I don't know if it's necessarily a callback, but at least it's coming full circle back to his original degree, which is particle physics.
Yeah.
Or I guess that's his PhD's in particle physics. I'm not sure what he got.
You got his
undergraduate.
PhD?
Yeah.
In physics? Wow.
He got his PhD in Caltech in physics. Feynman was one of his committee guys.
Wow.
Yeah, I remember an interesting anecdote from a while back. I'm not sure exactly how it went, but it was something where Stephen Wolfram asked Feynman what he thought about him making Wolfram Alpha before, when it was just an idea in his head. And Feynman was like, guys like us aren't meant to be making things like that. We're thinkers. And Wolfram kind of just ignored his advice and invented Mathematica later on.
There
I was
you
like,
go.
oh, Feynman was a non-believer.
Yeah, he was like, nah, it's all good.
Yeah.
He's like, just think about it. Somebody will make it.
Yeah.
Which is kind of like the position I think I would love to have in life. Just, I'll think about it. Someone will make it. That's such a. I mean, you really, yeah. Shout out to Feynman. But yeah, did you actually? I read a little bit of some stuff that's out there. I kind of wanted to. Well, actually, no. Let's just get into his background. Actually, so he got his bachelor's in physics, right?
I don't remember. I just remember his
so.
PhD was in Caltech.
But his PhD was in Caltech. Okay, so
I know he went to another college when he was younger and basically said lectures are bullshit. And it said something about him having no degree at Eton College. He might have, I don't know what he did, but I think he was kind of one of these child prodigies, since his Wikipedia basically said that he wrote 3 books on particle physics by the age of 14 or something. So
watched it all like in crayon or something. Like, it wasn't even like that deep. Yeah. I always take those callings as a grain of salt, because it's like you get to rewrite history when you're the hero.
Yeah,
you know what I mean? Yeah, I was cool too back then.
And yeah, who knows how in depth they were, but still pretty impressive if he even wrote a page on particle physics at 14 years old.
Yeah. Nowadays, it's like, can you imagine in the future when, like, say you're somebody famous, it's like, yeah, he wrote 2 pages of Wikipedia articles on so and so, on information theory or something. But no, that's cool. I mean, shout out to him. He's obviously a very intelligent guy. To have this idea, but I kind of wanted to dissect a little bit of
God, these flies are gonna get in the podcast.
His proposal.
Bastards. Sorry, go ahead.
His proposal on just like finding the theory of everything, because he's had multiple times to like go on multiple podcasts and talk about his theory, and then kind of.
Yeah, and let's also make it real clear for the audience. It's not he's not proposed a theory of everything. He's proposed a pathway towards discovering the theory of everything. Mm-hmm. So I mean, some of you might be like, "Oh, that sounds like bullshit. Like, what does that mean?" Yeah. But it's basically so Wolfram, as you probably know, Juan, but not sure about the audience. He's worked with like cellular automaton. Mm-hmm. So that's kind of what he's known. One of the other things he's known for. Another guy who you might recognize that is deep into that world was John Conway. I believe he just died of coronavirus.
Oh, shit.
But John Conway was the guy who invented Conway's game of life. And basically what it was, you can just imagine, well, I guess let me try to define it a little bit. So it's kind of hard to define, but if you just imagine, let's say a spreadsheet like Excel. Excel, as you know, is divided up into rows and columns, and they literally are called cells. Each of those cells that makes up, the row and the columns intersection. Mm-hmm. Let's just say you could turn one of those cells either 1 or 0, black or white. Let's say black or white. And cellular automata are given certain rules. So let's say if you had a row of 3 cells, mm-hmm. and you had a row of black, white, black.
Okay, hold on. Pause.
Yeah.
I don't like you using the word black. I want you to use the word cells of color. Okay. I'm kidding.
It's 2020 for Christ's
It's
sake. Huh?
2020. Come on.
Sorry, my bad.
No, so keep going. So we have cells of color, white, and then.
It reminds me of all these corrections that they're making right now.
Oh yeah. Anyway,
turning master into main. But anyway,
this is another conversation. So you have alternating cells like a checkerboard almost, like black, white. Okay.
Sure, but let's just say 3 cells.
Okay.
So black, white, black. So let's just give it the rule in our program that if we have a row of black, white, black in a row, then we change it to white, black, white. So with cellular automata, you can have some kind of space where you just randomly assign black and white to the whole spreadsheet. And then every time you see a black, white, black, you change those into white, black, white. And then from that, all of these interactions will happen, and you have this kind of automated process over time where it's a complexity can arise from these simple rules.
Yeah.
That's just an example I made up off the spot. I don't know if that would actually lead to anything, but certain things arise from those simple rules.
Yes.
And, this is kind of the basis as well of Wolfram's whole
computational theory.
His physics project here.
Yeah.
And except he uses something called hypergraphs in his theory. So it's still based on that very simple concept, just like in cellular automata. That's such a hard thing to say. But instead it's just a different kind of architecture that he's used.
Yeah. I actually thought it was kind of interesting because some of the images that are generated after these number of iterations from these basic set of rules produce stuff that look like neural networks almost, or they look, you know what I mean? Like he has a famous image of a hypergraph.
Oh, you mean from his theory?
Yeah. That looks kind of like a almost like a network of sometimes of what you see when you map the brain and stuff.
Yeah, you're kind of right. I didn't even think about that. But yeah, very true, because it's like these nodes, and they almost look like the lines that connect them are like axons.
Exactly, yeah.
Axons, is it called?
Axons.
Yeah. So yeah, I get what you mean.
It's really interesting stuff. I can definitely. I think the biggest leap here is connecting. I guess it's not so big. Once I was reading a little bit about what he was doing, I said, okay, maybe there's something to this,
Yeah,
like it applied to physics. I mean,
yeah, I kind of have the same thought. My thought is still kind of in the realm of I'm not really sure if this is really a pathway towards the theory of everything. But it's definitely something cool to look at that I think we can learn a lot from, and it yields things that have similarities to what we do observe in our universe with the same kind of mathematical structures, right? Yeah. Although I gotta say, I'm not sure if this structure that Wolfram has made, if you would come to those conclusions if you already didn't know things about special relativity or quantum mechanics, let's say, because this theory is supposed to yield quantum mechanics, special relativity, Einstein's energy equals mc squared equation, all from this hypergraph structure. I'm not sure it would be so clear if you didn't already know of quantum mechanics and general relativity, special relativity, and all that.
Right. Yeah. Because basically what you're saying is, does this theory have predictive power? Because you're saying that it's almost like he's subscribing, like, oh, by the way, like these little, because he did this. I was trying to read the part where he's talking about quantum mechanics.
Yeah, this is the part where so before the podcast was starting, I was reading this just to try to get my stuff straight.
Yeah,
and the quantum mechanics one, it's bad. I can't get it.
It is bad. It is bad. There's a whole paper written by John. I forget his name. But we'll probably put up a picture of it.
And sorry, bad meaning like I just don't know what the fuck is going on.
I took it as
I don't really understand it.
I took it as I mean,
there's been criticism though for sure of that one specifically.
Okay.
Because the thing about the quantum structure. So just to preface, one of these hypergraphs, one of these structures, actually is supposed to yield quantum mechanics. But in Wolfram's structure, basically the I guess the important aspects of it is that you actually have a singular universe, I guess, in some sense, like a deterministic universe.
Right.
And each of those branches,
Because he talks about like timelines. He talks about like the histories of moments and like how you're sort of like the superposition. It's sort of it's taking the interpretation of almost like it's not like many worlds, because many worlds does talk about like converging, like not converging,
diverging.
That
was my initial thought when I saw it, because the thing is, there's this aspect in his theory that seems to be a big backbone to his theory. It's called causal invariance, which I kind of like, because it's like basically saying, if you imagine 2 points in time, right? Point A and point B. He's saying that point A and point B, you can go from A to B, or let's say even you could go like A to B or A to C. He's saying that in his theory, basically, if you have A to B or A to C, even though if you go down A to C, it will still reach to the same end goal as A to B's path.
Yeah.
So eventually you can go through all these you can go through all these twists and turns, but eventually you'll get to the same end at the end, same answer at the end of the day.
Yeah.
That's a really broadly summed up version of it. Maybe we can explain a little more later.
He's saying it's like path independent, like where you get the result.
Yeah. So in his little nodal hypergraph structure, all the little twists and turns and divergences will end up at the same place eventually. So he calls this causal invariance, which is interesting because it means that basically it doesn't matter which pathway you go down, you're always going to end up in the same spot.
Yeah.
And then to me, that kind of did resonate as like a many worlds kind of deal. But even so, I didn't really understand it fully.
Yeah, because he said he's basically taking the idea from relativity or special relativity and applying it to quantum mechanics, right?
He's taking the same backbone of causal invariance.
Yeah.
Okay, we must have read the exact same.
Oh, maybe so.
Because I only read the special relativity in the quantum one.
Oh no, I read a little bit more about the quantum one just because I was trying to understand what the heck he was trying to say.
Okay.
And it's just I worry that it doesn't have predictive power. I think it obviously still needs more testing. My only concern with this all is that it doesn't how would you say, it just I'm forgetting my point now that I think.
Okay. Well, let me jump in then. So one of the things that I was thinking is you're saying it needs more testing power and it has lack of predictivity.
It looks like it.
Yeah, but I'm thinking it's just like it's kind of like a toy you can play with. It's less of a I guess that is kind of a model though, right?
Yeah.
But you have to know you have to, I guess, play with the toy more. So I guess if people have access to that toy that he has, then maybe you can get something from it. Because it also sounds like they came to a lot of these conclusions by playing with that model.
Yeah.
So it's just playing with these hypergraph structures and then applying certain rules to them to see what comes out of it.
Because this seems like they're retrofitting a bunch of stuff. You see what I'm saying?
I get what you're saying. It's not quite, though. It feels a little bit better than retrofitting.
Okay.
Because it is based on this really simple architecture of hypergraphs. And just to since I've been using this word so much, I kind of think I should define it. So hypergraphs are basically like these nodes connected by lines. So you could just imagine really simply, the example they give is like if you imagine a sequence of numbers. You have 1, 2, 3, and 4. So 1 is connected to 2, 2 is connected to 3, and 2 is also connected to 4. That would be an example of a hypergraph structure. So 1, 2, 3, and 4 are nodes, and then they have connections. And then what Wolfram does to basically the simple rule is he'll have something where he changes the connection somehow. So instead of going 1 to 2, 2 to 3, and then 2 to 4, he'll change the connection to something else to where maybe 3 and 4 are now connected, and some other things can happen. But it's all very basic, simple rules, and then he just runs this sequence over and over and over and over again until you have this massive hypergraph structure that connects in and back on itself in this weird three-dimensional shape thing.
Yeah.
And yeah, it's very abstract. It's like it's not even clear that this is the universe at all. This has anything to do with physics or the universe. But that's where I guess Juan and I kind of had problem with it, because it does seem kind of like retrofitting in the sense that who is to say, like, there's no real clear way that he came to the conclusion that these hypergraph structures should be made with the universe. But that can be okay sometimes. He just said the assumption that the universe has simple rules, therefore I'm going to use a simple hypergraph idea to make big complex or to make complex things. Complex things from simple rules, just like the universe seems to be this complex entity from simple rules. So that's really the connection that there is. No more than that, I guess. I mean, it's kind of a leap, but at the same time, I guess it's fine though, right? Like, why not, right? It's something to explore.
Yeah, you're allowed to do that.
Yeah.
You know?
It's kind of like, you can almost say it works sometimes. Like, think of how Descartes, ascribed the vis vivo, as we talked about in the energy episode. Like, they were using literal sacred arguments, like religious arguments, that God is a perfect entity, so he should have this conserved life or living force in the universe. And that's how they came up with the concept of energy, essentially. It was basically a mystical conception, and it actually turned out to be something incredibly useful for physics, probably one of the most useful concepts in physics. So
dang,
it works sometimes. I can't knock it.
You can't. I mean, this could be a first approximation to something bigger, that's my concern, that it's more of a simulation of sorts. And but I mean, it's fun. I mean, it's cool. It's actually a really neat idea, and I think it probably it'd be interesting. I wonder if it'll take on more of an interpretation role than
actual discovery role.
Maybe
so. Because the thing is, I worry it's not really clear like what your goal is when you play with this model of hypergraphs, because it's like playing with a toy almost, to me. It's like a sandbox toy in many ways. Like, it's not clear like what, to me at least. I don't really know. I'm not an expert, of course, and this isn't my field, but it seems like he knew of relativity and he knew of quantum mechanics, so he knew how to manipulate the hypergraph in such a way to yield those things. It's not so clear that you're going to be able to just start from first principles and immediately come up with some way to like connect, let's say, relativity and quantum mechanics.
His argument is that you'd be able to reverse engineer if you get a result, right?
Yeah, that could be interesting.
Yeah, because that's kind of what his argument is, from what I've seen. Like, say if you were to be able to accurately predict a lot of results in quantum mechanics, then you can just reverse engineer and say, oh, well, this is why. This is it. Because it sort of seems right now as a sort of interpretation of sorts, kind of like, what's his name, the Everettian sort of approach.
That's the many worlds.
Yeah, I wonder if any of this has, like, is this testable in some way? Like, would his findings be
predictive, you mean?
Predictive, yeah, or even testable in some sense, where it's say if he like says, oh, it looks like quantum mechanics is based on maybe two sets of rules, of iterative rules, and and then you sort of maybe. Then your job as a theorist is then to think, well, what could these two possible rules be? And then, of course, then you hand this over to the experimentalists, and then they try to hammer it out. But that's one of my concerns. I don't know. And actually, one of the interesting things that this whole thing kind of made me think about was obviously quantum mechanics and relativity, but it had to do more with... I wonder why we have such a hard time dealing with or merging these two in our known physics, like quantum mechanics and general relativity.
Yeah,
because
I would imagine maybe because relativity has the weird property that gravity is the bending of space time.
Yeah,
and then also with quantum mechanics where everything is like a particle, and then quantum field theory that extends to fields.
Yeah. Well, his
I'm
theory.
not sure why that. I didn't take QFT.
Yeah.
And I don't know general relativity at a high enough level to really say what the broken pieces are.
Well, like he did say something about how the presence of energy sort of causes in his model causes like bends.
Mm-hmm.
So you see the same thing in his model with general relativity or whatever, and it sort of is analogous to the presence of energy still. It makes the system, it perturbs the system in some way. And it made me think a little bit about like why maybe we can't detect maybe even like the theory of like having gravitons, right?
Mm-hmm.
And it made me think deeper about like can we even begin to tear the fabric of like our sort of the matrix that we're in, like, you know what I mean, by like experimenting on it? Like, can you really probe it down to that level, like
to the level of like, let's say, detecting a graviton?
Yeah, because I think the energies that are posited out there, like to the orders that are just right now completely unachievable. Like we're talking like 20, it's like 10 to the negative 22 or something, EVs or something. I don't know. Something incredibly small or something. Mm-hmm. I'm throwing a number out there that's probably not right. But
yeah, you better be careful when you're throwing out numbers. But
I'm not a particle physicist, so.
But yeah, I think the fact that gravity is so weak just makes it so incredibly difficult to do anything with, right?
Yeah.
Like we barely just detected gravity waves like, what was it, 2 or 3 years ago or something?
No, probably 10. It just seems like that because
is it really 10 years ago?
Probably, yeah.
No, because
right?
it
LIGO detected.
It happened during while we were in graduate school.
Oh, okay.
Remember, because we were in
quantum
class.
Yeah.
It's not 5. It's like 4.
Okay, 4.
Okay, 4 something years. Dang once. Don't make me feel that old, bro. But and those gravity waves were literally like 2 giant black holes or something colliding.
Yeah.
And they barely just detected it. So it's like, to imagine us trying to detect a graviton just seems completely impossible.
I know. That's why I was like, it's so crazy.
Or at least if it ain't going to happen within a very long time from our deaths.
Yeah, but I don't know. Wolfram, I was watching an interview where he was like, well, you know, you can think of space as a continuum, and then I was like, well, he's completely, and he even said as much. He's like, you know, physicists thought the graviton, you know, might not exist or doesn't exist or whatever. Well, physicists think the graviton exists, but he's like, it doesn't, flat out.
He claims it doesn't.
Well, he's just like, there's no evidence of it. And he's just like,
True.
well, we can think of space. True, right?
Yeah.
But
well, that's kind of a...
I think it helps his theory because his theory is very continuous and there's no discretization of sorts, right? Mm-hmm. There's like, everything is kind of in a continuum.
Right.
So,
it's a little bit of there's a disclaimer on that, though, because he's claiming that there's no evidence of gravitons, but it's like, if you can't even probe for gravitons, then... But I guess you can say, because it doesn't really align with any of our theories, there's no place for it seems, but...
Well, there's a place for it, but it just doesn't...
There's no strong evidence, we'll say.
Yeah.
Okay.
I don't know. It's just, for me, it's always like... you always get to those sci-fi scenarios where it's like, oh, you do detect... I wonder if it's like a cascade effect of sorts if you detect from those watching like sci-fi movies, where it's like, oh, you have enough energy to like break the fabric of space-time and then you cause a cascade effect and destroy the whole universe.
Well, hopefully we're long dead by that happens.
It's like, oops. And then before you know it, it's like, well, you don't get a chance to say oops. You just evaporate into nothing.
Hey, at least it's painless. And by the way, Juan, do you have the time, man? Because I forgot to start my clock.
Yeah. It's
okay.
We're almost at 30 here.
All right. Well, you just let me know.
Yeah. But yeah, yeah, it's kind of funny how it's just kind of funny how that happens. Like just the catastrophic thinking that certain movies go to. With things like this, like just scientists. I don't think scientists have this level of power. I mean, I guess a lot of those people that make movies now, they probably saw scientists in a bad light because of World War II, right? World War One.
Yeah, I mean, and these things do happen, right? Like scientists do fuck up. Look at Chernobyl.
Yeah.
Look at Fukushima. Look at shuttles, space launches. Like scientists, they do mess up sometimes, right? Like it's like a lot of these things take a whole bunch of things to go right, and people just don't understand the level. People don't really understand when things can or can't go wrong unless you're really into it.
Yeah.
And deep in that world. Like the LHC, physicists weren't really scared, but of course, some physicists talking to a reporter probably mentioned the fact that the energy scales are on the order of black hole, on the order to create black holes.
Yeah.
And then a reporter's like, wait a minute.
That's where you got movies.
You saying you can make black holes?
Yeah.
And if I remember correctly, black holes consume everything around me.
Yeah.
But they're like, oh, it'll just evaporate because of Hawking radiation.
Yeah.
So it's like, yeah, physicists can make these errors, and scientists can make errors, right? And the general public doesn't understand when the error is a little bit far out or when it's more close to reality.
Yeah, they just hear black hole and are like, "What the?"
Yeah. They're like, you didn't mention that before.
Yeah. This is why you guys are stopping us from getting funding and stuff. You know, you're not doing your due diligence of, communicating it effectively in some ways.
It can be hard sometimes, though, right?
Sure.
And also, some people may communicate things poorly. Like, I remember the classic. I don't know if it was a blunder, but I remember one time when some guy they found some exoplanet or something that was similar to Earth, and they asked some scientist what the probability of it having life on it, and he says 100%. And I'm like, God, it's like when physicists get excited, they say dumb shit sometimes too. And I know the guy was probably just really excited.
He's like 100%. There's a probability of life existing.
Yeah. There's 100% probability that is associated with finding life on that planet.
I think maybe that's what he meant. Maybe he took it literal and was just.
I think he was just excited because he found an Earth-like
Yeah.
planet that had water on it that was relatively our size in the Goldilocks zone, and he said some stupid shit.
He's like, what about planet Nibiru? What about planet X?
Is that the 10th planet?
Yeah.
Eddie Bravo.
Yeah.
Eddie
yeah.
Bravo.
Look it up.
He's literally got a gym called 10th Planet Jiu-Jitsu.
Look it up, folks. I'm just kidding. Don't look it up. You don't want to do any of this. But yeah, it kind of brought me to a point where you would get. I wonder. I don't know. Which one is more of a true scientist to you? The person who takes on or tries to test these ideas? Because there's a lot of people in academia that would look at Wolfram's theory and say, that's a waste of time.
Yeah.
But then there's some. I mean, I would probably put myself in this camp if I was a paid academic. I would probably investigate this. I'd probably just see where it goes.
Yeah. Yeah.
Where would you lie on this camp?
I think I can be in both, honestly.
Nah, don't fence it on this one.
Okay, let me think. So what do you mean, though? Do you mean like which? I guess I could. Let me just make my own interpretation then.
Sure.
So what I would do naturally.
Mm-hmm.
It depends also. Since I'm an experimentalist, I probably wouldn't go this route. So if you're talking about in real life, I probably wouldn't go this route. But if I was a theorist, I might.
Let's just put you. Let's just say you don't have risk of losing your job. Would you try to investigate something new?
That's not a factor. It's just mostly a matter of, am I doing experimental physics or am I doing theoretical physics?
Yeah, but as an experimentalist, you can do this. You can.
It's not really useful for an experimentalist.
But would you want
it's
like?
Not the path I would
but
go.
let's just say that this is a new emergent theory on how to describe the universe.
Yeah.
Would you investigate it in a meeting with some intention of adding, or if you could add to it? Because this could be
at its present state. No way.
Mm-hmm.
It just isn't strong enough in its predictive ability. It's not convinced me really at all. There's no real experimental predictions even made, so that'd be almost like a 0% chance I would waste my time on it.
Yeah, because I think a good theory in general, it can tell you what it can predict and tell you what it can't predict.
Like Einstein's relativity literally said, like, you should be able to observe this much curvature around this star due to gravitational lensing. Like, he has clear experiments that you can easily do as an experimentalist. It's just like it's so well laid out. It's like, oh, like how can I ignore that? Literally, if his theory is wrong or right, all falls on this test right here. So to me, that's a sign of a strong theory. Higgs said that if you can reach these energy scales, you should literally see a particle of this kind of size, this kind of spin, X, Y, and Z. That's a very clear experimental prediction. Wolfram's theory is not like this. It's just a pathway towards building more theory on a, I guess I guess he's trying to use it as like a roadmap to try to find what the potential theory of everything could be, the rules. But it's not very clear.
Yeah, because it's like a
toy
symbolic.
to me.
Yeah, it's like a symbolic roadmap.
Yeah, it's extremely abstract. It's like almost in the highest levels of abstraction, very far away from experimental realization. So, if I was a theorist, I might be interested because then it's like something to play with. It's a toy to play around with. You can mess around with the nodes. It's cool because it's all computational. Like I could definitely see myself getting into that as a theorist. But as a theorist, you can kind of fuck around like that and it's not so bad for you. It's like you can maybe glean some information from that, and even if it's useless, you can maybe get some new kind of computational tools or mathematical tools from that, and you still kind of win in the long run. So you got to use your time wisely, right?
I think it's worth investigating, though. I think a lot of these new kind of propositions, this is because we don't really have a lot to go on right now.
Yeah, I think you're right. I think it's definitely useful.
Yeah.
And I like computational stuff because I think one of the big cornerstones of modern day physics is computational. Like I think if you're going to be a modern day physicist, a theoretical physicist, you should be kind of proficient in programming and using computational models.
Yeah.
Like to me, that's kind of the forefront right now because, no other era has really been able to use computers at the level that we can use them at.
Yeah.
So to me, I'm like, if you're not really using computers, you're not really doing things to the highest level you can in theory.
Do you think you could build a human computer?
What does that mean? Huh?
That means you have an army
like
of
man?
let's say you have
Bicentennial man?
No,
Sorry.
let's say you have like an army of people. Do you think you could build a computer to do if you tell each person to do a computation?
Oh, yeah. In theory, you can build you can build a computer out of anything if you can have a 1 or a 0 state. So like a person raising their hand or is a 1 or a 0.
Yeah, I wonder back then, like in Egypt, say the engineers needed to do calculations.
Don't let Eddie Bravo hear this podcast. It's going to be a new theory of how they build the pyramids.
Yeah,
they use human computers to do the calculations.
They use an army. They used to lay out the army, and then they had the generals do the calculations, and then so.
Yeah, you can literally build a computer out of anything as long as you can make a 1 or 0 state, right? You can build a computer out of this book.
Yeah,
this
yeah.
faces up and this faces down 1 or 0.
Yeah, you can. So
my hand is the literal input, so you can build a computer out of anything, man.
Yeah, it's true. For those listening, this is a very rudimentary argument on how to build. I guess maybe some people it's not exactly obvious, is it?
It isn't at all.
So maybe we should. Maybe we should
many years to understand that.
Maybe we should explain it to the listeners because it's like this how to make computations, how to, By the way, I feel like algorithm was one of these words when I was coming up.
Yeah.
That were very vague and ambiguous.
Yeah. I think you're right.
You still think it's like that?
Somewhat, but I think it depends on how deep you are in it. I think algorithms kind of clear when you're on the surface of programming and things, but when you start to get down to like quantum programming and these kind of things, then it starts to get a little bit ambiguous.
Because I was going to say algorithm to me is more of it's just code. You know what I mean? It's just a line of code.
A set of instructions.
For...
It's a recipe.
Yeah.
A cookbook is an algorithm.
Yeah. So just
in some sense.
So yeah, we should have probably done this in the beginning, just to kind of tell people what the hell we're talking about. Maybe like algorithm, but like also talking about computation. Like how do you build a computing machine?
So really, a computer just needs to have some kind of input, I guess, and then some kind of output. And you just need a 1 or 0 state. You need to have at least a binary system. So you need to at least be able to turn something on or
It
turn
could be
something
like
off.
black, white, or
Yeah, sure.
yeah.
Anything like that. Like, and then you have to, I guess you have to be able to build at least arithmetic from that, or, actually you don't even need to go that far advanced. You can just say, as long as you can build a NAND gate, then you should be able to build
And
an
NAND gate
arithmetic logic
is-
unit. A NAND gate would be, and so like an AND system would be this. So if you have a 1 and a 1, for an example, for your state. So let's say I had 2 books and I had a 1 and a 1 state. If I can read that output as a 1, then that means that is it. That's one output in the logical rule set, and then a 1 and a 0 would give me a 0. So both states have to be the same. I think a 0 and 0 is also 1.
So 0, 0 in your
I
book
forget,
in your
though.
book picture would be like no books. Or
Sure.
the 0 and
Or
1
a
would be
upside
one
down
book.
book or something.
Oh, okay, sure.
So I was saying like the cover of the book would be a 1, the back would be a 0.
Gotcha.
So this one, the cover is up, and the cover of this one's up, and then the back of this one's up.
Okay,
So
but
that's
for
a 1 and a
listeners,
0.
he's just saying to but let's make it simple. Let's just imagine like a book, the front is the 1 and the back is the 0.
Yeah.
Like you said, it's a binary system, but
So then I know my output is 0 for that if that's an AND
Right.
gate.
So what do physicists usually use? I guess why do engineers use electronics for that?
Okay, so electronics are useful because then you can actually get a bit for your output, right? So with my
does that mean?
system of books, or I can get an output, a value output. So with my system of books, I can see clearly that I have 1 and a 0, right?
Mm-hmm.
But there's no output being sent.
True.
Like there's nothing that's going to
There's
make
no
it do
signal.
anything,
Yeah.
right? Maybe if I had this attached to something like some kind of Rube Goldberg machine or something, but generally the nice thing about electricity is, let's say if you can build an actual AND gate instead of a NAND. A NAND is just the opposite of an AND. It just can't. It flips every output bit
It's
to
not an AND.
the opposite one. Yeah, that's what it is. Literally, not AND.
Yeah.
So with my book system, though, there's no output that actually happens here.
Yeah.
I need to actually make it have some kind of output mechanism. So let's say if I have like this book here, and and I flipped it, and then a lever pull or something. But with electricity, you can make it when you have your AND gate so that you have a 1 and a 0, you get no current out. But then when you have a 1 and a 1, you actually have some kind of output current. Sometimes I've noticed this. I think they give this example somewhere. I read it. That you have in real life. I've seen in my house. So like you'll have a light switch in your house, or a light in your house that has that's controlled by 2 different switches. So when you flip one switch, the light turns on, and then when you flip the other switch, the light turns off.
Yeah.
That is an example of a I think it is an exclusive OR or something. Damn it! I wish I would have.
That's like
a
circuit. That's like a circuit where they're both sharing the same. Like one of them is open, one of them is closed. So if one of them is open, the other one is closed, and vice versa, right?
Yeah, I forget
Right,
what it
'cause
is
you're saying,
exactly,
like-
because it's like if they're both up, they can still be off.
Yeah.
But I can't remember now. I don't want to talk and say the
don't
wrong things because I haven't
complicate
thought about it.
I don't think we need to complicate it.
Yeah,
at
and I don't
all.
want to sit here. But that is an example of like a real life, really close to like what a computer can do.
Mm-hmm.
So it's hard to imagine with the book system, but with that light analogy, if you guys want to just take your time to think, because I don't want to just sit here in thought on the podcast, but if you guys want to take your time and think about it on your own, you can write down the logic for that, and you'll see what circuit it is supposed to be. If you look up logic gates and just match up the what is it called, the table?
Yeah. Oh, the actual name? I have no
Yeah, it's called like a truth table. Yeah, you can check the truth table and see what logical circuit it is.
Oh, I see. Yeah.
That's a really close example to what computers are made up of. But you can make a computer out of anything.
Yeah, they take it to the next level where they actually use electricity, right?
Yeah. Like
And
we
those-
could hook these books up to levers and strings and whatnot, and
Yeah.
we can still make a computer.
Yeah, but modern computers use like chipsets, right? So they use like these basically Man, I totally blanked on the freaking name.
What does it look like?
No, just like
describe it.
the silicon, the silicon based MOSFETs.
Yeah.
You know, field
Metal
effect
oxide
transistors,
semiconducting
field
effect
transistors,
transistor.
Yeah. So like, have we done an episode on field effect transistors?
Probably not. I don't think so.
Wow,
Maybe we
that's
touched
interesting.
upon it, maybe in like smartphones or something, but
No,
I don't think we
probably
did a
not.
full.
I don't think we
Okay.
did. But the field effect transistors are the basis for all of our modern technology, pretty much.
Mm.
But it's based on this thing where you have the material of interest,
Yeah.
right? And that serves to, or that has basically the properties necessary for your like logic gate, essentially.
Right. That's
So-
like the height of what this representation system that we have, right? Because it's like super small, it's nanoscale size, and it can actually take an input and output electricity on something that's super small, and then you can build that up into an actual computer.
Yeah. So the reason why we go smaller too with these processing units is because as a computational machine, you want to pack more processing power, meaning you want to pack more of the computational units
Right.
in one small piece of space.
Mm-hmm.
So you want a material that's both that can actually register or have a low enough electricity threshold to process your electric input.
Mm-hmm. Mm-hmm.
And then number two, a
Because
material
it's less energy usage.
Yeah. So for you, it's like realistically, that would be your phone having really good battery life because
Right.
the processor doesn't take that much power.
Right. Which is, I think, why they use ARM processors, which we talked about, I think, in the smartphone episode.
Oh, what are the ARM processors?
So that's the ones that have like all of the units in the chip itself.
Oh.
So like it'll have like the GPS on the chip.
The GPS, the GPU, you mean?
The GPS.
The GPU, right? GPS.
The GPU, and then there's a GPS unit, I think, on there, isn't there?
Why would the need? Well,
the
I'm saying. Yeah, I think you're saying global positioning.
Yeah,
system.
I am.
Oh, you are.
Yeah,
Why would
because
they
there's a
need
GPS unit that needs to be on the chip.
Oh, for the phones, yeah, dude.
Yeah.
I'm thinking of processors, like.
Yeah, you're right though, because it's like the chip actually has the GPU, the GPS unit.
Oh, okay, gotcha.
All of the gyroscope, all that stuff on there, whatever it is.
Yeah. I was thinking about the PC. I was like, why would they need to put a GPS unit on your PC?
No, because you can already get location from Wi-Fi and you're not going anywhere.
I know. That's why I was like, what the hell are you talking about?
No, so actually, but I think there is ARM processors being used in PCs more now. I think a buddy of mine was telling me that Apple was switching to ARM now or something. I guess it's because people don't really care to have all that stuff separate from the chip now, and it's just easier.
Makes
and
sense.
It's good enough, right? But
yeah. But yeah, you typically go for something that's that has a low threshold for electricity, and then also something that can withstand, or just basically has the properties where it can expel heat efficiently, so that it doesn't just basically what you call ohmic heating, which is like, you know how when you pump current in something,
sure,
it heats up and it's linear. You want something that's not linear. You want something that's rather like...
It takes a lot to heat it up.
Yeah. There's a specific name for this. This is why we were talking about aluminum one time.
Oh, yeah.
Remember, because we were like, why is aluminum used in everything?
Yeah, like why does it not get hot and I can touch it when it comes out the oven? Yeah.
It's so funny as physicists, like, where you know about the property of something, but you don't know the name.
Right.
You know what I'm saying?
Right.
We're like
thermal conductivity, I think.
Yeah,
right?
yeah. Or like heat capacity or specific heat capacity or whatever. But anyway,
I always forget those confused. Specific heat and heat capacity, because
think-
they're almost the same.
Yeah, one is extrinsic and one is intrinsic.
Yeah, like one has a unit to it, right?
Yeah.
Yeah. I think so. That's specific heat. I want to say because it's specifically.
Intrinsic. Yeah. Yeah. So, but yeah, all this engineering now at the modern technology level is the basic concept of this logic gate of like flipping and whatever, doing that. And you and I used to work with devices too. So yeah, this is something that I think we're both sort of familiar with. At a fundamental level. So. Yeah, but more on the materials side.
Yeah.
Yeah.
Our overlap in research was pretty similar, I would say.
Yeah.
Although we did pretty different stuff, but we're still working on the same kind of shit ultimately in some ways.
In the abstract, yeah.
Yeah.
Yeah. But yeah, modern computation, it's loosely based on this whole discussion with Wolfram. So,
Yeah, we kind of deviated a little bit. What's our time, by the way, Juan?
I think we're 50. Yeah,
okay,
we're
50. Yeah,
But,
do you want to touch up on Wolfram a little bit at the end now and like
Yeah,
on his
what-
relativity?
His relativity thing?
Yeah, so I read his relativity one, which is kind of interesting.
Oh, really?
Yeah.
Oh, I didn't even. I read it too, but I didn't really.
Yeah, so the relativity one actually made a little more sense.
Yeah, I didn't see any problems with that.
It was hard still to understand.
What do you mean?
Because so what he basically did was his hypergraphs were still there once again, and he said that if you imagine instead of hypergraphs though they called it strings. So strings I would imagine is just like the computer version of string, where you have a set of characters. So like he would use the example of like A B B B A or something. That would be a string of characters, and each of those strings you can perform on an operation on it. So let's say they give an example, I think in his paper, of he has a string of like BA, 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 BA alternating like 10 times, let's say. So 10 sets of BA, BA, BA. And you can change that BA into AB. So if you imagine a whole row of BA, on the next row you change every BA to AB. And then on that next row you change all the BAs to AB. And eventually you're going to get this pyramid structure. We could maybe put a picture on the podcast. You'll get this pyramid structure for every time he changes the BA to AB. And then what they do is they make a simplified model that shows that this is where I get a little bit confused. So there's connections between the operation. So the rule. So the rule is when you switch BA to AB. So and actually let me just show you so you can see a picture. So the rule is
Oh, I remember this. It's like he just makes a basic. He makes you have like a set of numbers or set of string or set of characters, and then you have a basic rule where it like even swaps them or something.
Yes. So let me try to find it. So it's right here. But so what he does is this. So
yeah, he it's. I didn't. This is why I kind of glossed over it because it was a very his explanation of special relativity. I didn't really see any big headaches from it. It was like okay, it's a nice little thing.
yeah, this was the most understandable one for
Yeah.
me, but it was still not understandable. But I had it probably like 70%. I feel like. So yeah, so you see the yellow. He has the yellow nodes. I guess that is the and I'm going to try to keep it good for the audio listeners as well. So those yellow nodes are the rule. And he connects the yellow nodes with blue lines. And those blue lines are apparently the like time between those rules. So if you change one of those BAs to AB, the yellow node is that flip. And then he connects a yellow node to a yellow node with a blue line. And then that blue line is the time it takes to do another flip.
Yeah.
So you can arbitrarily set any point in time to when you do another flip.
Gotcha.
So then what he does is he makes a bunch of lines which he calls foliations.
Yeah, okay, this is like way too abstract. I'm trying to get to the meat and potatoes.
Yeah, it's not so bad though. I'm trying to set it up a little bit so I can understand.
Oh, okay.
So it's like these foliations are just intervals of time. So from node to node, let's say if you go from yellow node to yellow node, then you're going in time. So the vertical axis would be time.
Yeah.
It's kind of like a Minkowski diagram in a lot of ways. I came to the
it kind
conclusion
of
of because it's like the vertical axis is time,
Yeah.
and then the horizontal axis is space.
Yeah, he's basically recreating these diagrams.
Yeah, he
the
basically is
Minkowski
like
space diagram.
recreating the Minkowski space in some ways, just with a different kind of rule set because it's based on the causal invariance, which is the whole motivator behind this structure. But then what he's saying is this is kind of an interesting part where he says that if you just go from node to node, then that's the equivalent of no change in time. But then if you're actually going somewhere in space, then that's when you have an actual shift. That's when you're actually moving in time. And
And
depending
you can
on
see
your
it in
velocity.
the diagram. Yeah. You can see
Yeah.
it goes from a straight line to a slanted line.
Yeah.
So if you're an audio listener, this is basically like a network. So you can look at your space and time as like a cone, in a sense, right? He's still taking.
You're using
from
the Minkowski.
Yeah, but this is sort of analogous to what the Wolfram picture is showing.
I don't
but
know if it's completely analogous though. This is why it tripped me up because I'm not sure if it is.
Yeah, I know, but this is easier in the sense for the audio listeners to kind of get. Like if you imagine like a square network thing that you're looking at. Let's say
It might be better to keep it in 2 dimensions as well.
Yeah, let's say you're looking at like a checkerboard, right, in front of you.
Mm-hmm.
You turn it diagonally so that diagonal is like kind of like going out from you, right? This is what we're seeing. I'm trying to describe to the audio listeners what we're saying here.
Okay.
But yeah, it's like you're pointing the diagonal edge at your point, so it looks like you have a diamond in front of you.
Okay.
And this is basically what it's showing you. It's showing that like if you draw a line directly bisecting that diamond sort of shape, you're going in a straight. Time is the inertial time, right? This is kind of what he's drawing here.
Yeah.
And
I don't know about the description.
No, but I'm saying like
I think it's making it more complicated.
No, but that's what he's doing, right?
Yeah.
Yeah, and then like if say you're deviating from that line, he's kind of saying that you're basically going to change. You're going to have some dilation of sorts where he's basically just describing his picture.
So he basically, to long story short, I think it's going to be very hard to try to describe, especially since we don't really understand it to a full level. Let's just go ahead and just sum it up. The basic thing is he derives the gamma that we use for time dilation or length contraction, which is just 1 over the square root of 1 minus beta squared.
Yeah.
And beta being the velocity over speed of light. So it's like a very geometric kind of diagram that he creates here to derive, quote unquote, the special relativity constant, which is how he claims that he gets special relativity from this.
Yeah.
But for me, it's like I'm not really sure. I really like the whole backbone of causal invariance from this, though, because that kind of gives you something new to play with. And he uses that as well in his quantum derivation as well. So I guess I don't know about his other theories. Like he has another derivation of E equals mc squared. And then even I think he tries to connect space-time and general relativity. But I imagine causal invariance plays a role in those as well. So I guess one of the big takeaways with Wolfram's model is that these hypergraphs have this causal invariant property, which yields these physical models of the universe.
Mm-hmm. Yeah, he's taking like causal invariance as a principle.
Yeah. And actually, I don't even know if I could say it yields the physical model of the universe. It just yields models that have similar properties to physical models that we already know are true or pretty damn true. Mm-hmm. And it's also interesting because, he gets the gamma not using speed of light as an axiom. So his axiom is causal invariance. So for us, usually we use setting the speed of light to be c as the axiom for physics, relativity, and then that will give us, length, time dilation and length contraction. But this one, he uses just the causal invariant hypergraph structure to actually get that gamma.
Yeah. Yeah. I mean, he's kind of already, like I said, it just seems like a lot of like he already knows the answer and he's like making it fit into his little model, his little toy.
It's like a in between. Like it's kind of like it's like a little bit of reverse engineering / retrofitting with a mixture of like interesting new axioms, specifically the causally invariant axiom. Yeah. So that's why I kind of like it, because it's kind of like it gives me the same feeling as like a Schrodinger equation. Like Schrodinger literally just made up the Schrodinger equation because he based it around the wave equation, right?
Satisfied units. He took it out. The wave duality principle.
Yeah, he knew Planck's constant had something to do with something in quantum. He knew that the wave equation had something to do with waves, and he knew that particles had this wave particle duality. And he's like, I'm just going to make this equation, and I hope that this is probably right. Let's see what happens.
Yeah.
So he did that. as we mentioned earlier, Descartes literally said that there's this visa living force that exists in the universe that should be conserved. He did that, and it turned out to be right.
Yeah.
So you can get away with doing that stuff sometimes.
Yeah, this is why, if you're a PhD student and you're actually like trying to investigate, or if you're thinking about doing something interesting, your advisor would probably not let you study this at all.
Yeah, he wouldn't.
I don't
be
think
happy.
any advisor would ever advise you to use,
unless he was already in this field or something.
Right, unless yeah. I mean, you just
they probably wouldn't be happy because the results.
Why?
The results may not come. It just seems these kind of projects are not for like grad school.
That's what I'm saying.
Like you need to have actual things that are more reliably done.
You're probably already a professor who has tenure.
Yeah.
And is probably playing with this and gathering, maybe deeper principles, like you're saying,
Right.
causal invariance.
Like, this is why I think like we talk about Eric Weinstein in this podcast. Eric Weinstein had no advisor for his PhD defense.
Mm-hmm.
And they literally didn't want to give him a PhD because I think he was doing things related to his geometric unity theory of everything. And they're like, what the hell is this kid doing? This is just some random road that nobody knows anything about, so they don't know if he's doing anything properly or not.
Yeah.
And
I mean,
mind you,
that is-
Eric's a smart-ass guy, but it's like,
But that is kind of a problem, though.
yeah, I get it.
Because it's like if you're an advisor, you're like, dude, the hell are you talking about?
Yeah.
You know what I mean? Like,
Yeah, and it's also not really feasible, right? Because then it's like if the advisors have to learn all of you, they have to like buy into your religion now. Like they have to learn all of your terminology, all of the discoveries you made. It's just not feasible. Like nobody wants to do all that. They need to do something that's more closer to what they are already familiar with.
Yeah. Yeah, and it's kind of an issue. I think this is a problem. I didn't know this about Eric, but maybe this is more indicative of like where his behavior is from. Like kind of like why it took him so long to propose something.
Yeah,
Because there's a little bit of a criticism. He doesn't like the criticism maybe, or he doesn't like to receive.
I don't think he's got a problem with criticism.
Objections and of sorts.
I think he doesn't like academic structures in academia.
I could see that.
He's
but,
more of a outsider guy who likes to do his own thing.
Yeah, but like looking at him like not having a committee, because the committee is there to criticize your work in some way.
Well, he had a committee, but no advisor.
Oh, well, your advisor's there also to kind of criticize your work in some way.
Yeah.
So it's
Well,
like
your advisor's also there to lead you down a particular path.
ideally, basically, you're looking at somebody with experience.
Yeah.
And that they can guide you through pitfalls or maybe
Right.
even like logical like mishaps or something, or maybe even like just kind of steer you away from trouble.
Right. And just to give you guidance.
Yeah.
But I guess Eric felt like
Kill it.
he was independent enough where he didn't need to do any of that.
Yeah.
I get it, but at the same time, it's like I get both sides. I'm like, Eric's a smart guy. I think it's cool that you can do your own thing, but at the same time, it's like any sufficiently advanced theory, it's like you have to start learning people's terminology and things, and you can't really know if they're even bullshit or not until you actually kind of know something about it yourself. Like with Wolfram's theory, I had absolutely no conception of what it even meant or anything until I looked into it. Like, I don't know if it's bullshit or not, and the only thing I have to go off is the track record that Wolfram already has. And you say, oh, it's probably there's something to it, because I know Wolfram is a guy who actually does real things.
Yeah.
But until you look at it, you really just don't know, right? And it's so far out of my area. It's just like,
Yeah, because he's another. But this
know.
is why you're looking at another guy who like is coming up with his own set of rules and like,
Yeah.
terminology, and
Yeah.
you're coming into his world.
yeah, you've got to kind of buy into their religion a little bit.
Yeah, I wouldn't say religion, but yeah.
Yeah, I call it a religion because it's like when you're starting a new theory, it feels almost like a religion at first, right? Because you don't even know if it's real.
Oh, gotcha.
You know, it's not the same as well-established knowledge.
Yeah.
Well-established knowledge has like 20 different pathways to get to that result.
Gotcha.
People have fleshed it out to such a level, it's so damn convincing. You're just like, this cannot be wrong.
Yeah.
But when you have new stuff, it's almost like, am I wasting my time? Because if some guy's crazy and he's making some dumb points, or if he doesn't look, if he's if he misses some critical things about a theory he wasn't aware of,
Yeah.
then you just bought into the religion and it's not right. It's religion essentially because now it's just
that's
bunk.
true. This is a problem with a cult. Well, this is how cults form, right? I think the psychology of cults is like you build a
No,
world.
I think cults are low level.
Well, you build an insular like world, and like
that's kinda
you
true,
create
yeah.
your own terminology and like rituals and shit.
Yeah. Until people are so invested that they're like,
Well, now I can't
this,
leave.
yeah, like this can't be wrong, or else I've wasted so much time of my life that, you know.
Rest in peace, string theorists. This is basically.
Yeah, I know. Basically, right?
That's the perfect what is it called?
Yeah,
the perfect
analogy.
comparison of
Yeah.
what a scientific cult looks like. They've got a lot of
like
useful
space
things to
bomb.
come out of it, but it's
Yeah.
like, if it doesn't pan out, you feel like you're wasting your time. Like the guys who came up with the ether, that guy had to waste a bunch of time doing that shit, right?
Just
People who came up with supersymmetry
Yeah.
and string theory in that realm, they might have wasted a bunch of time. It's just the reality of it. It's like you have to explore that stuff though sometimes.
Yeah. Because I mean, like I said, would you investigate it? I probably would if I was a professor and I had free time and I wasn't afraid of getting fired or something. I'd be like, yeah, let's see where this goes. Maybe study it and then see if it's bullshit or not, right?
Yeah. Especially if I was already computational.
Yeah.
Because then you can just use all your computational systems, and I'm sure Wolfram made it. I mean, I don't know if I'm sure, but I would imagine Wolfram made some kind of easily portable
Yeah.
computational engine or system to be able to do this, to
Yeah.
be able to play around with it.
I would just refrain if any of you theorists are out there. I would refrain from if I have a good ass theory like the guy who proved Fermat's last theorem, right?
Yeah.
He
Wiles, Andrew.
Yeah, Andrew Wiles. He spent a decade creating the formalism for it and everything. Came out, was wrong the first time. Embarrassingly
Yep.
held a press conference and
And
everything.
then made a completely new theory
Yeah.
in like what?
I think a year's time or
Okay.
two or something. Or two? Was it two?
I don't
know.
remember.
It basically was a shorter amount of time, but this is because he had the community helping him.
Mm-hmm.
And this is kind of the point of science and discovery. You advance it. That's why you have the peer review process, because
Yeah.
it helps move things along quicker. Helps
Right.
advance the study a lot quicker. Because if you're just withdrawing information and you're saying it's not done, it's not perfect, and it's just like, no, you're throwing the idea out there to kind of like get some feelers. Maybe some people will latch on to something that is important,
Right.
an important principle, and carry it to its like logical conclusion,
Exactly.
and then reach an interesting result, right?
Science is not done in a vacuum.
Yeah.
Even though it is experimental, but you need to have science is social, despite what many people may think.
It is true, yeah. I have friends who are outside of science who say that they're like, "Wow, I didn't think your field was so social," but I'm like, "Yeah, you interact with, you discuss and converse and have arguments with people about certain ideas, and we'll talk about problems that we're looking at. We'll talk about edge cases, things like that. It's a lot more social than you think, or at least that's the whole thinking process behind it. You're there to solve problems, like either you have an ego and it's just you go at it by yourself, or
It can be done sometimes, but it's like good luck making your life more difficult.
I know, but it's because we're a lot less inclined to be antisocial, I think.
Yeah.
But
I mean, I say by all means, if you're a Grigori Perelman type guy, hey, do what you got to do. What you want to do. That's the guy who figured out the Poincare conjecture. He literally lives with his mother and just did math for years, and then solved the Poincare conjecture with some Navier-Stokes knowledge or something.
Yeah. Props.
I'm like, hey man, if that's you, go ahead.
Is it the Subway guy?
No, that was a different guy. He's Chinese, I believe. But he solved his working at Subway.
Yeah.
The prime number sieve. But that wasn't actually solving a millennial problem. It was just getting closer to the twin primes conjecture, I believe.
Amazing.
Yeah. But still, you can. That's so. It is possible.
It is. But I'm saying, put your best foot. Actually, don't put your best foot forward. Just put your foot forward.
Yeah.
Sometimes.
Right.
Just see if you can give it a
Two
shot.
minds are better than one.
Yeah, because like I said, you run into less problems of criticism, because if you just front load everybody with this textbook here's my theory of everything. People are just gonna be like, I'm not gonna read that.
Right.
Too long, didn't read.
Like, what's the guy that apparently solved the ABC conjecture or something?
Don't remember. This was a couple years ago, right?
Yeah, several years ago.
Yeah.
Some guy who potentially solved the ABC conjecture. I haven't heard anything since, but it was like this long ass manifesto, and people were just "Really, bro? We gotta read this long ass shit."
This is what I mean. This is exactly what I mean.
Yeah.
There's a level. There's a psychological element to it.
Yeah. Like, nobody wants to waste that much time if your shit's wrong. Nobody wants to read an 80-page paper if your stuff is completely wrong. It's just like, you got to convince people.
Yeah.
Right?
Piecewise. Take it. If you make a discovery, let it out at once. And you're just afraid that somebody's going to take your work and make it better or something. But hey, like, you'd be the founding person.
Right.
You know what I mean?
Einstein almost lost general relativity to him. What's the guy?
A couple mathematicians.
Yeah.
I think like 2 or something.
Hilbert or something?
Hilbert.
I don't know.
I think it was Hilbert, was it?
Yeah, I feel like
I think it was like 2
Hilbert.
mathematicians that at the time.
He's like, literally, I'm going to do this in like 2 weeks. And Einstein was like, fuck. I need to get this thing finished.
I mean, Einstein even says, embarrassingly enough, that it took him a decade to like.
Because he sucked at math.
Yeah.
Einstein sucked at math. He was a physicist, straight up. But all the mathematicians who were fucking
elites.
Like, ooh, this is easy.
Yeah, it's just like, oh yeah, dude. I think he came back. Was it Hilbert? I forget who it was, but they came back 2 weeks later, and they actually made his theory more rigorous with the math.
Oh,
like, it was way better.
I can see that.
And Einstein was like, well, shit.
Who cares though? As long as Einstein got the credit in the most of the stuff.
Yeah, don't let your ego kind of get in the way of progress. Okay.
Yeah.
So. Yeah. Anyway,
what's the time?
We're at an hour 10. So with that, folks, we kind of went all over the place, but I still think we kept a common thread.
Yeah.
Along.
Mostly Wolfram.
So yeah, leave us a comment.
Stay for the outro.
Yeah.
What's up, guys? Thank you so much for watching. So
Thank
that was
you.
a little bit of a longer one.
Yeah,
but not by too much, but
nah.
Yeah.
No, over here, sleepy Juan over here.
It's a little bit dreary.
One. I look probably a little sleepy.
Hopefully the color correction will make your eyes pop a little bit more.
I know. I'm going to have anime eyes. Can you put anime eyes on me?
Yeah. That might be tough. Might need some machine learning or something from Wolfram for that one.
Konnichiwa.
But yeah, guys, thanks for watching. Like, subscribe, share, comment, all that good stuff. Check us out at Eigenbros on Twitter, Eigenbros on Instagram, Eigenbros2 on TikTok, and Eigenbros.com. And we will see you guys next time.
Peace.